So what are the requirements for this technique? So what are the assumptions that we're making and on which we hope to base a correct estimate of this regression line? Well, the regression technique assumes the following. First of all, the variables have to be numerical. As I said, you can use it with ordinal ones at your own risk. Okay? The second one is that the relationship has to be linear. If by looking at the correlation coefficient and or the scatter plot we don't see a linear relationship, there is very little point in doing an estimation of the regression line. Yes, we will come up with a regression line, but whether that line makes any sense whatsoever, we don't know. In fact, there are many examples that can be constructed where the relationship is really non-linear, and very tiny changes to one of the observations involved can create a really wild change in the regression line itself. And therefore, how good is it? Next, the variability once again has to be all in the output. And now you can figure out how complicated that is, because in many situations we are simply observing two variables and both of them end up being random. So this assumption basically is telling us, well, assuming that we could have chosen the x's as we wanted as opposed as they came up, then everything else we're going to say is valid. This is again an assumption should be in the back of your mind. It does not really do much in terms of invalidating the estimates that we get, but it does really make us wonder, is this the proper technique we're using? If in fact there is random variability in both x and y, why should we have y be a function of x as opposed to x be a function of y? Okay, so that's something that you may want to look at in some situations. For instance, is it the amount of insulin that determines the blood sugar, or is it the amount of blood sugar that will determine how much insulin you're using, right? So that's the kind of the questions that you may have to answer in some situations. And remember that this technique only assumes variability in one, not the other. Finally, the errors that are also called residuals. So the size, the length of those squares that you see in front of you, the distance between each of the observation and the line that we have constructed, again, they're called residuals. They should have a normal distribution, bell-shaped distribution with a mean of 0. So here is another situation where this normal distribution comes in. And if it does not exist, exist in the situation we're analyzing, then the results that we come up with may not be valid. Finally, the data have to be homoscedastic, and that is what? What does that mean? Well, let me explain to you what homoscedastic actually means and what impact it has on linear regression. So this concept of homoscedastic actually has to do with the pattern of the variability of the data. What we're looking for is pretty much a pattern of data that has to look like the one you see right now. So the least square linear regression assumes this kind of pattern that you see. Well, what's so special about it? Well, what's very special is the fact that the data are mostly within a strip. Okay, so they tend to go up or to go in the direction they go not only linearly but also with a variability which is the same throughout the range, throughout the strip. So when we look at the vertical variability, remember that's what we're assuming that the variability is vertical. Only in the y component, it shouldn't change much for different values of x. Okay, so this is what we call homoscedastic, so same variability. That's what the word actually means from, as you can imagine, Greek, right? Now, what we don't want to see is heteroscedastic data, so different variability. And this can come in several forms. The three most common ones are the following. You can have data that looks like this. Looks innocent enough, doesn't it? But if you notice, the data here are not spread along a strip, but they're actually spread out in a sort of football shape, right? The variability starts being small, then it gets bigger and bigger, the vertical variations get larger and larger, and then it gets smaller and smaller again at the other end. Or we might have this kind of pattern. In this case, the variability has the exactly opposite shape. So it's almost a funnel kind of situation, or double funnel, where the variability starts large, gets small in the middle, and then becomes large again. Or, quite simply, the data could be like this. In this situation, again, we are not having our data spread out in a strip, but in a fan kind of pattern. Okay, so once again, the variability gets bigger and bigger as x gets larger and larger. So in this situation, we don't want to use, or we want to be careful on how we use linear regression, because its results may not be very reliable. So, are there other regression methods besides least square linear regression? Well, of course, you bet your life there are. Now, first of all, when the linearity is missing, that's fairly easy to do. Okay, what you can do is you can use other kinds of regression, things like quadratic regression, logarithmic regression, exponential regression, polynomial regression, etc., etc. There's a whole bunch of the different types of regression computations that can be done, and they're not that very difficult to do. In fact, many even basic computer and calculators have computer programs and calculators have programs to implement any one of these non-linear regressions. The other thing that people do quite satisfactorily is to actually transform the data. So instead of using the data as they come out of the observation, you apply some transformation to them so that the resulting data then become linear and homoscedastic and all the things that we're looking for. So again, you may see some in some articles mentioning that they've done some kind of quadratic or square root or logarithmic transformation to the data. And again, one of the reasons, probably the most common reason, is in order to come up with data that actually does have the kind of requirements that are needed for linear regression. This is a very legitimate technique. It's not cheating. It's not sort of twisting the data for our own purposes. It is to using mathematics in a proper way. Of course, it has to be done properly, because there is also a wrong way to use them. And if you don't know what you're doing, then probably you're going to end up with the wrong conclusions. But again, it can be done and it exists. Now, another situation where the normality of the residuals is missing, okay, so if the residuals are not normally distributed and there is something else going on, then there is something else that can be done as well. Oh, and by the way, what I'm going to tell you also apply in other situations where some of the other assumptions are not made. What people do sometimes is they use either non-parametric versions of linear regression, or they use things called factor analysis or other classification or prediction methods. Remember that one of the basic purposes of constructing a linear regression or regression line is to be able to have a formula that given x will predict y. Well, if we can make that prediction mechanism, we construct that prediction mechanism in some other way, well, then we have achieved our purpose and we don't need to worry about anything else. Well, there are many methods that do that, and they do it through ways which do not involve constructing a formula. They use different methods. Again, we're not going to go into there, but if you run into any article that talks about factor analysis or other such things, you may want to look them up a little bit.